creators of the Java libraries realized that doing everything with thread and wait and notify and synchronize really wasn't the right way to do things. And for that reason, in Java 5, they introduced the java.util.concurrent package, which is a library of various classes to help with doing concurrency. We want to talk about this some, even though in reality most of the time you would want to use the Scala classes instead, but there are some things that appear in java.util.concurrent that do not have a Scala equivalent, and that can be useful to you. So we're just going to kind of do a brief coverage of the whole thing. So we have the package java.util.concurrent. It has two sub-packages called atomic and locks, which we will come to later. Kind of the cornerstone of the concurrent library is this concept of an executor service. And an executor service has several methods on it. The ones that we're going to care about, though, are the methods to submit tasks and to shut down the executor service. So the task itself, it could be a runnable. A runnable is just something that has a run, like what we put inside of our threads previously. Or it could have a callable. So callable is a type in java.util.concurrent, which, unlike runnable always gives back a unit. The callables have a call method that gives back a type v. So we can have these return values to us, much like the futures in the Scala libraries. Indeed, you'll note that when you submit, you get a future. Now, this is not a Scala future. This is a Java future. And at least the base future does not have nearly as many options for what you can do. Starting with Java 8, they introduced a completable future, which is a subtype of future, and it actually has many of the methods that we would expect in Scala that allow us to compose things. Unfortunately, it does have the methods in future which allow us to do things that would be blocking and that we shouldn't do that much. So, the problem that I want to explore here is actually taking the product of a whole bunch of numbers. So previously we were taking the sums of many numbers, but all of these numbers were doubles. And for things like ints and doubles, they're built into the hardware of the machine and they go very, very fast. And so even a million of them happens very, very quickly. Instead, I've made these types big int, and I'm making 50,000 of them, and then I'm going to take the product of them. Now these numbers are between 10 and 20, technically 10 and 19 inclusive, 10 and 20 exclusive. When I multiply 50,000 of those numbers together, I get a number that has at least 50,000 digits in it. Okay, so this is a very large number, and in order to store it accurately, I have to use a big int. Int and long aren't big enough. Double would store it, but I think actually double might not store it. But even if it did, it wouldn't store it accurately. Okay, we'd lose a lot of digits. So using a big int gives us full accuracy. It also makes it much slower, and that's kind of what we're going for here. So to illustrate this, I wrote a method called timecode. Now timecode takes 3 arguments, and it's curried. The first 2 arguments are an integer called warmups and an integer called timed runs. It turns out that the Java virtual machine actually optimizes things if they run multiple times. So this warmups is how many times you want to run it without timing it, kind of to warm up the system and possibly optimize things. And then timed runs is how many times we want to run it and time the result, and this gives us back the average of those times. So here I am calling this, and I'm just using the built-in product and then the built-in product on a par. And if I run this, you'll be able to see there actually is a speed difference between these two. This is a slow enough operation. For this to happen sequentially takes about 0.36 seconds. Now these numbers actually jump around, but this winds up being on the order of 0.3, and the second one winds up being on the order of 0.2 or 0.02 or less. So there's a significant speed benefit on the computer that I happen to be running on, which actually has a whole bunch of cores, which is part of why it can get such a large speed increase. Now, the sequential version is kind of slow, so I'm going to comment it out. What we want to do is we want to write some other versions of this, and in particular we want to start by writing one that uses an executor service. Now, first we have to figure out how we get hold of an executor service, and it turns out We don't create them directly. We use this class called Executors, and Executors has inside of it a number of methods like new fixed thread pool and new cache thread pool. We're going to go with the fixed thread pool, where we can specify exactly how many threads we want to have. A cache thread pool will keep making new threads if it doesn't have any that are available, and it will reuse them. I want to specifically fix my number of threads. I've created a constant here for that number of threads. Now note that this par does not care about that num threads. It is using however many threads it feels like, which on my machine it might decide that it wants to try to use 48 of them. But we're going to limit this, and that way we can vary that constant to see how that affects performance. So we're going to bring in executors, and we're going to make a new fixed thread pool of our num threads. And now we want to make a method that will multiply an array of big ints in parallel. So def parallel product that takes nums, which is an array of big int, and it returns a big int. Okay, and I want to borrow some code from what we did over here, because a lot of it is going to wind up staying similar, except this isn't threads. Remember, when we call submit, we get back a future. And so instead of new thread, I am going to say es.submit, and I'm going to pass it a new callable of big int. Now a callable of big int has to have inside of it a method called call that returns a big int. So let's make a var prod, which is a big int of 1. We will wind up giving back prod, and we will change this to be prod times equals. We need to import callable and see how close to happy that is. Okay. Let's see. Oh, we have an open parentheses right here that we need to match. There we go. Okay, so now it formats nicely, and it's just unhappy because it's supposed to give back a big int, and we're not right now. Well, it turns out the Java future has a method in it, a blocking method called get, which is much like doing a join and then getting back the result. And it makes our code easy to write at this point. So we can do this. We can say futures.map to get, and then just call the sequential product on that. And I actually want this to be plural, so I'll change the declaration point. And there we go. So parallel product uses our executor service. I need to shut down my executor service, otherwise this application will never stop. And we can test this by doing a timecode call. And we are going to call parallel product on small ints, and we run it, and there you can see it works. This version happens to be slower than what happens in par. So we have no knowledge of how par breaks up the work here. It is still much faster. It's not quite 10 times faster, but it's a lot faster. Of course, it couldn't have been 10 times faster. Let's try this. I've argued that I have a machine where it could decide it wanted to use 48 threads. Let's give it the option of doing so. Notice that didn't really help. It's actually kind of interesting to play with this, in that if you do one thread, yeah, that's a little bit slower. Okay, that's actually very close to the sequential time, and there's enough variance in there. We go to 2 threads. Now, if we got perfect speed up, we would expect this to drop to something like between 0.2 and 0.15. So we run it, and yeah, that was really good speed up. What about 4? 4 again, almost cut it in half. 8. Okay, I didn't see another factor of a half there. 16. No, we've kind of bottomed out here. We'll come back and we'll address that, the fact that there is a point of diminishing of returns, and in this case it's somewhere between 4 and 8 threads. We're not gaining anymore, and we're clearly not going as fast as par. We'll talk about why we might not be going fast as par in the next video, and we'll also talk about why this bottoms out, and we'll look at some other potential implementations for how to write this function.